Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll look at stochastic gradient descent and look at the details around what is gradient descent, how it compares with stochastic gradient descent. We'll match mini batch gradient descent, and we'll then look at how the intuition behind the SGD classification and regression, and finally look at some tips before closing this video. And in the next video we'll do the actual implementation in the Python. So what is gradient descent? If you remember, in the previous video we looked at loss functions. So in machine learning we have a data set on which we train a model, and the trained model, what we try to do is find the optimal values for the parameters. And why we need those optimal values for parameters is because those values then give us the predicted value that is closer to what the actual value would be. And to get that value closer to the value of the actual value and the predicted value as close as possible, we we need the difference between those two values to be as small as possible, and that's measured in terms of loss. So here on the right hand, in previous video we just have the two-dimensional plot for the loss curve. Here we have a three-dimensional plot with two parameters, w1 and w2, and on here on this vertical axis we have the loss. And this is shown here by the contour plot, which is like a funnel, open on the top and then it curves down here at the bottom. So as the value for the loss is uh, high up here, the values for the parameters w and w2 would not be optimal. So what always the aim of optimization algorithm is to find this spot right at the bottom of this loss function, which is right here. And the idea is that that particular lowest value corresponds to optimal value of the parameters w1 and w2, such that when we use those optimal values of parameters, we would then get the predicted values which are as close as possible to the actual output values. So when we look at this particular plot from top, this is what we would see as shown in the left hand side. So the outermost oval in this particular plot represents this top edge of that particular contour plot, and the innermost circle represents this bottom part of that particular plot. And these are the values for these are the axes for parameter w1 and w2. So now once we have that, another point I want to make here is another name for this would be batch gradient descent, where the batch essentially means the entire batch, the entire data set. So that's also a batch gradient descent. Now let's imagine a point on this particular loss function, denoted here by the red color x. The idea then is we begin optimization with this value of x, which is nowhere close to the lowest loss. It's the highest loss we have, and it's the least optimal values for the parameters. Now as we move through the iteration, as we iterate through the optimization algorithm, we slowly start approaching the minimum, and finally we reach the global minimum, which is the lowest point in that for that loss function. And once we reach that point, we have the optimal values for the parameters. So that's how the gradient descent works. and we'll look into further details as to how it moves through one point to the next point. But before we do that, let's look at how stochastic gradient descent is different than in the earlier case. Whenever we move from one point to another point, the optimization algorithm runs through the entire training dataset for each data point. However, in case of the stochastic gradient descent, that's not the case. Here, the algorithm just uses one sample or one row or one instance of the dataset to calculate the new value of the parameters to move on that loss function. And as a result, the there is, while it approaches the minimum, the move is a little erratic, so it could go down and then go back up and then go back down, go sideways, then come back down, but eventually it will reach the global minimum. So that's one of the difference. Now if we try to compare again the batch, mini batch and stochastic together, the main difference is that in batch you process the entire data set each time. Mini batch, however, it's the best. It's a compromise between these two, where stochastic runs one sample. In mini batch, you run a mini batch. Let's say we have 100,000 records or 100,000 samples or rows in a data set. Then what a mini batch would do is it will run the optimization only on 1,000 rows, then update the W parameter, and then run on the next 1,000 rows, the next mini batch, and then update the parameters. Whereas for the batch, it's running entire set, and for stochastic, it's selecting the next sample. And thus, finally, we have either of these algorithms would then reach the optimal, give us the optimal parameter. Now the update rule for the parameters is shown by this equation, which has two main parts. One is this one, which is the previous value of the parameter, and then this part right here, which is subtracted, either subtracted or added to this particular previous value to take the next step. And how fast we want to move along that uh, loss curve, loss function, is decided by this parameter, which is the learning rate. So smaller learning rate means we step very slowly. A larger learning rate, which means we step much faster to that loss function. So this term here has the regularization term here in blue, and then we have this loss function, and we are taking a partial differential with respect to W in these two cases. Now to simplify things, I've substituted this term right here by just saying loss. Now if you are familiar with calculus, you already know how the slope works, but if you are not familiar, that's okay. I'll try to give you an intuition of how that works. So let's say if we calculate the slope of slope at this particular point on the curve, and if the slope is a positive number, it means that the line direction of the line shown here in magenta is like this. It is in, as the W increases, your loss is also increasing, so that's the line. And so when we have a positive number here, when you multiply it by the running rate, essentially we'll have to subtract that number from W, and so then next value of W would be a lower number, and so we'll have to move back on this x-axis, and so the next point would be somewhere here. On the other hand, if we have a negative number, negative value from this slope, then minus will become plus, and so therefore the value of w1 would the updated value will be larger than the previous value, and so we would move from this point to this point. So we are moving on the right side towards the right side of w, and therefore this would be a larger value. And so this is how the uh, the parameter values are updated until the minimum is reached. As we talked about earlier, if the learning rate is small, then uh, there will be very small increments, and thus it will take a longer time to reach the minimum. However, on the other hand, if the steps are too large, then it could overshoot, and the algorithm could fail to converge. So both of these are have their drawbacks. And so what you want is a middle ground where you have the optimal learning rate, and that can be found out by cross validation. So SGD in Scikit-learn also has average SGD. What average SGD means is that when we update the parameters at each step, it is the average of all the previous values for parameters, as opposed to in just regular SGD, uh, the updates are done based on just the previous value of the parameter. Now, the SGD has the SGD classifier and SGD regressor. So the SGD classifier here shown in this figure is similar to the linear support vector machine when the hinge loss is used. And so to explain that, I've used this figure, which is same as that was discussed in the previous video. So here we have two classes. So this would be a binary classification problem. Let's say this is the positive class, this is a negative class, and we have a maximum margin that separates these two classes. So we want a maximum margin, and these two dotted lines are those that denote the margin, and these points on the margin, they are the support vectors that satisfy the equation for that margin. And these are the losses that can be used with the SGD classifier. We can also, if I read correctly, we can also use the regression losses with the SGD classifier. And the penalties, we can use all the three, L1, L2, and elastic net. Now, if it's a multi-class classification problem, then it uses the one versus all approach, which we have discussed previously in other video. The way that would work is let's say we have three classes, then one class is considered as a positive class, the two other classes are considered as negative class, and then a binary classifier is fit on that, and so on for the other two classes. You set other class as plus positive class, the remaining two as negative class, and then run the binary classifier. So each sample is run through the three classes, and then the classifier that gives the maximum score, the data is classified to that class. In the regressor, as we have discussed in previous video, the uh, the idea is in this case, if the epsilon insensitive loss is used, then the idea is that uh, it is the zone between these two dotted lines around this line, which is given by this equation, where as the value of epsilon uh, increases, as the error increases beyond these values for epsilon, then there is a penalty imposed on those data points. So as long as the data points are within the epsilon insensitive zone between these two dotted lines, then there is no penalty associated for those data points. And the docs also suggest that if the number of samples or number of rows or number of instances is greater than 10,000, then we want to use the SGD regressor. Else we want to use the ridge, lasso, or elastic net. The stopping criteria for SGD, there are two. We can specify early stopping as true or false, and they stop on different uh, criteria. So here the train, and if it is set to true, then the input data is split into train and validation state, and then the stop is based on the score of the validation state. Whereas if it's set to false, then stop is based on the objective function, loss function. And if if the criteria does not improve, then the algorithm stops. Also, if the maximum number of iterations is reached, then also the algorithm would stop. And these are some of the tips again from the docs. For SGD, you want to scale the data set. So as you'll see in next video, we are going to use the standard scaler. Then to find this regularization parameter alpha or the learning rate, you could use the grid search CV or random search CV. And then for setting the number of iterations, maximum number of iterations, they suggest using this relation. So let's say if you have 100,000 examples, then you'll use this 1 million divided by 100,000 and then use those many max. And if the features are those that are extracted after a PCA, then the average L2 norm of the data set should equal to 1. Finally, if the number of features is large, then the documents also suggest that the average stochastic gradient descent works well. And to use average SGD, all you need to do is specify average is equal to true when using the regular SGD, either classifier or a regressor. And then the complexity for SGD is given by this big O notation here, which is KNP. So number of epochs multiplied by number of samples multiplied by a number of non-zero features. So as the input size increases, the number of operations would increase a lot, and so that would mean the computational resources required would also increase. Finally, let's look at the code snippet. Here I've imported NumPy, linear model, standard scaler, and make pipeline. And the difference in this particular implementation is that I'm creating here pipeline, so make underscore pipeline, and we are scaling the data set using standard scaler, and then using the linear model .sgd classifier to use. So when we perform the fit, the data set would first go through the scaler, and then it would be fit, and then the classifier would be fit on the data set. And finally, we have the clf.predict to predict on the test set. That was it for this video. I hope in this video you got some intuition about what is gradient descent, how it works, and how stochastic gradient descent is different from regular gradient descent or batch gradient descent. And finally, we also looked at how what is the scope of SGD's classifier, SGD regression, what types of loss functions can be used with each of those. In the next video, we'll look at the actual implementation in Python. Until then, please like, share, and subscribe. I hope to see you all in the next video. Thank you.